today we will study the knapsack problem using branch and bound. So what the problem says here is, given n items of known weights Wi and values Vi. So here the weights are represented by Wi and values are represented by Vi, where I takes the values from 1 to n because there are n items. A knapsack of capacity W is given here, and we need to find the most valuable subset of items that fit into the knapsack. So here we will see there are 4 items given, so n equal to 4. Then each item weight is given here and its corresponding value is given. For example, item number 2, its weight is 7 and it is giving us the profit as 42. For example, item 4, it's weighing 3 kg and it's giving us the profit of $12. So here, given these 3 column information, we need to calculate value by weight. Right. So 40 by 4 is 10, 42 by 7 is 6, 25 divided by 5 is 5, and 12 divided by 3 is equal to 4. So this column is calculated by using the second and third column. So the first column represents item number, second column represents the weights of each of the item, third column represents the value of the item, and fourth column represents the value by weight, that is information. Here, out of these 4 items, we need to pick one item, we need to pick number of items to the knapsack in such a way that it should fit into the knapsack. So here, the knapsack capacity is given as 10. So capital W equal to 10. So this capital W will indicate the total capacity of the knapsack as 10. So pick the items in such a way that the total weight of the item should be less than or equal to the total weight of the knapsack given, which is 10 here. So we'll try to solve this by using a branch and bound technique. Here we are going to make use of one formula so as to calculate the value of the upper bound. So UB equal to VI plus W minus WI to V of I plus 1 divided by W of I plus 1. So this is the formula used so as to calculate upper bound for each of the items. So here we are dealing with a maximization problem because we want to get more profit out of this so as to pick the items and put it in the knapsack. So those items should give us the more profit. Such items you need to select for the knapsack, and it has to satisfy the constraint. Pick the items from the given set of items in such a way that they should fit into the knapsack and should provide maximum value. So for that we are going to make use of this formula so as to calculate upper bound because we are looking at the maximization of the value. So upper bound is to be calculated. We are going to draw the state space tree, the first node of a state space tree. So here, this is 0th node. Make 2 compartments. In the first compartment, you are going to write the weight 0, W equal to 0 and V equal to 0. When none of the item is selected for the knapsack, then W equal to 0 and V equal to 0. We need to calculate upper bound for this node by using this formula. So UB equal to, here I will calculate the value, UB equal to VI, V0 plus capital W is 10 minus small w is 0 into, when we are at 0th item where W equal to 0 and V equal to 0, here V of I plus 1 by W of I plus 1 will indicate the value by weight profit of the next item. It's V of I plus 1. we are calculating upper bound for V of I and W of I. That is item number 0. So this ratio is the ratio which is calculated for item number 1, because it's V of I plus 1. V of 0 plus 1 is 1. W of 0 plus 1 is 1. So V1 divided by W1. V1 divided by W1 is 10, because it is the value by weight ratio for item number 1. So put that value here, it is 10. So upper bound for this is 10 into 10, which is equal to 100. So UB is calculated for this node by using that formula. This is equal to 100. Next, we need to branch this node and calculate the upper bound when item 1 is selected. So we'll say width 1. When we select item 1 for the knapsack, we'll write it as width 1. And this side, on the right side, write without 1. Without 1. When item number 1 is selected for the knapsack, its weight is 4 and its value is 40. So here we'll write weight equal to 4, W equal to 4, and V is equal to 40. V is equal to 40, because we are dealing with node number 1, and node number 1 is when we select item 1 for the knapsack. Its weight is 4 and its value is 40. That's what is written in the note here. Now we need to calculate upper bound for this. So how to calculate upper bound? Again, make use of this formula, put the values, and then get upper bound value. VI. What is the VI value here? It is 40. 40 plus capital W is 10. 10 minus WI is 4. It is 4 multiplied by V of I plus 1 by W of I plus 1. So here I is equal to 1. 1 plus 1 is 2. 1 plus 1 is 2. So V2 divided by W2. V2 by W2 is the value by weight ratio for second item, which is 6 here. So that 6 is to be multiplied. This is equal to 40 plus 10 minus 4 is 6 into 6. This is equal to 40 plus 36 equal to 76. So 76 is the upper bound value for this node. It is 76 here. Let's calculate the value for this. W equal to 0, see, when we say without 1, we are not selecting item 1, right? So value of W and V are going to remain same. W equal to 0, V equal to 0. It will carry forward the parent value, because we are not selecting item 1 for the knapsack. So this level we are writing for item 1, whether it is selected, not selected. Selected, it has given us the value for the upper bound is 76. And now we will calculate the value for the upper bound when the item is not selected. When that item is not selected, upper bound value will not be this value. Now this value changes. So how to calculate the value for that? V of I, it is 0 plus capital W is 10 minus small w is 0 multiplied by, see, I am talking about item 1. So I need to consider item 2 value by weight ratio. Item 2 value by weight ratio is 6. So multiply this by 6. When you multiply this by 6, 10 into 6 is 60. So I calculated upper bound for this node as 60, which is different from this node. Why we got different value here? Because here we were dealing with none of the items selected for the knapsack, but here we are dealing with one item selected, right? Selected, not selected is written. When it is without 1, then W equal to 0, V equal to 0. I have not selected any of the item for the knapsack, so that's why it is without 1. W equal to 0, V equal to 0, but value by weight ratio changes here. When I am at 1, I need to consider next item value by weight ratio, which is 6 here. So with this 6, I got 60 as the upper bound value, so that is written here. Next is, out of these two, the one which will give me the maximum upper bound is to be explored to the next level. So it is this. So explore this for the next level nodes. So now I want to include item 2 for the knapsack. So I'll write with 2. With 2. So when it is with 2, the second item, its weight is 7 and value is 42. So right here, W equal to 7. You are not writing 7 directly here. This 7 is to be added to the previous weight because already I have selected one item for the knapsack which is satisfying the consent. Now I want to add one more item. That weight is to be added to the previous weight here. So previous item weight is 4. Now I want to select item 2 whose weight is 7. So 7 plus 4 will become 11 and 11 is greater than this 10. 11 is greater than 10. That's why I'm not going to calculate upper bound for this node. This node is called as non-promising node. Right? Also you can say non-feasible, not feasible, or else not feasible or non-promising node because the total weight is greater than knapsack weight given. So this is called as non-promising node or not feasible node. So we need to explore the node on the other side. So this is without, I'll write in short WO for the without 2. If I don't select item for the knapsack, item 2 for the knapsack, then it will carry forward the previous, that is the parent weight and value. Previous node weight and value. So this is W equal to 4, V equal to 40. W equal to 4, V equal to 40. Now you need to calculate upper bound for this. So again, the values in this formula, upper bound equal to this V is equal to 40, upper bound equal to 40 plus W is 10 minus this small wi, weight for the second item which is 4, to 4 here, into the weight by value ratio of the next item is selected. Next item is item number 3 in this case. So we are writing level 2 node is for item 2. With, it has given me the non-promising node. Without I am writing. So when I am dealing with node 2, next item, so multiply this with 5. Now this is 40 plus 10 minus 4 is 6 and 6 5s are 30. So this is 70. Upper bound value for this is 70. So at this level, only this node is available for exploring to the next level. So explore. So node number 2 finished. Next node 3. The nodes at level 3 is to be explored. So here I need to write the option for with 3, with item 3 and without 3, right? So here with 3, third item, its weight is 5 and value is 25. And these two weight and value is to be added to the previous node here. Previous node weight and value. Previous node weight is 4 and item 3 weight is 5. 4 plus 5 is 9 and 9 is less than 10. So those two, if I select item number 1 and item number 3 whose total weight is 4 plus 5 9, 9 is less than 10. I can fit those two items into this knapsack. So it's the constraint. That's why I'm going to calculate the upper bound for this node. So W equal to 9. Why it is 9? This weight equal to 4. 4 plus 5 is 9. Here is V equal to 40. 40 plus 25 is 65. So I'll write V equal to 65. V equal to 65. Now you need to calculate upper bound for this node. Put the values in this formula. V of I, current B is 65 plus capital W is 10 minus small w is 9 here, 9 multiplied by, when I am dealing with third item, next item ratio, which is 4. So multiplied by 4. This is equal to 65 plus 1 into 4, 4, and this is 69. So 69 is the upper bound value. 69 is the upper bound value. What about this node? You need to explore all the nodes of each of the level before going to the next level. That's what the branch and bound says. Without item 3, so without 3, I already have told that it carry forward the parent node weight and value. So W equal to 4 and V equal to 40. W equal to 4 and V equal to 40. Now I need to calculate upper bound for this node. Upper bound value for this node. So here, sorry, value is 40, V is 40, 40 plus capital W is 10, small w is 4, multiplied by, when I am talking about the third item, the next item value by weight ratio to be considered, 4 here. So it is 4. This is equal to 40 plus 10 minus 4 is 6, and 6 4s are 24. 24, and the value is 64 here. Upper bound value is 64. So out of these two, obviously the left side node is giving me the most upper bound value, which is 69. So that node is to be explored to the next level. So the last level node, because only one item is left out for the selection. So I'll write here with 4 and without 4. With 4, with item 4 and without item 4. With item 4, item 4 is here. Its weight is 3. The 3 is to be added the previous weight, which is 9. 9 plus 3 is 12. And this weight is greater than the knapsack weight given, which is 10. So that's why this is promising. This is not feasible node, because the total weight of the items is exceeding the knapsack capacity. In that case, it will become the non-promising node, because it is violating the constraint given. What is the constraint? You need to pick the items for the knapsack in such a way that they should fit into the knapsack. Means the total weight of the item should be less than or equal to the knapsack capacity given, and should give the more profit. But here the total weight is 12. This 12 is greater than 10. That's why this has become non-promising node, or you can say not feasible node. I need to explore this node now without 4. So when it is without 4, obviously it will carry forward the weight and value of the current node. W equal to 9 and V equal to 65. Now you need to calculate the upper bound value for this. Value is 65. So this is 65 plus W minus WI. Capital W is 10. Small w is 9. 10 minus 9. When I am selecting, not selecting item, when I am talking about item 4, no next item is present here. No next item is present. That's why we will consider value by weight ratio of that node, of that item as 0. So here it is 0. Right. I am writing for level 4, which is for node 4. Item 5 is not available, but here I need to write weight by value ratio of next item. As next item is not available, I am going to write 0 as a ratio value. So 0 here. So 10 minus 9 is 1, 65. It's 0 here because you are multiplying with 0, it's 0. The result is 65. So here UB equal to 65. All the 4 items got over. None of the item is left out for the selection. So here your state space tree completes. It ends here, and this is feasible, optimal solution. This is the optimal solution. Optimal solution is the solution which is feasible and which gives us the most cost in this case. So here B equal to 65 and upper bound is 65. So it has given the upper bound value equal to 65. So if you trace this particular tree, see here we need not have to explore this node. This is also non-promising because here this node has given me the upper bound value 65 and here it is 60. You need not have to explore the right part of this tree, not required here. Now you need to write the items selected for the knapsack. Items selected for the knapsack. This is equal to C. Just go to the optimal solution, backtrack. This is without 4. 4 is not included. And this is with 3. We got this node with 3. So right here 3. Third item we selected for the knapsack. So to arrive on to this result, we selected third item. Next, backtrack. Second is not selected because this node is without. Backtrack. Item 1 is selected. Right? Item 1 is selected. So these two are the items selected for the knapsack. 1 and 3. Only 2 items selected. So when I traced this particular tree from bottom to top, I came to know, see, this is the tracing. Right? This from here to here, from here to here, and here. This is without 4, with 3, without 2, with 1. Only with are to be considered. With 1 and with 3. So 1 and 3. These are the 2 items selected for the knapsack. And what is the total profit earned or value gained? It is item 1 value plus item 3 value, which is 20, that is 40 plus 25, which is equal to 65. And here is the value, which is 65. So this is how the knapsack problem is to be solved by using state branch and bound. Right? So this is a state space tree. When none of the item is selected, it is node number 0. This is called as node number 0. Right? This is node number 1. I'll write in the circle. This is node number 1. This is node number 2. This is node number 3. This is 4. This is 5, 6, 7, and 8. 8 node is the optimal. It has given me the optimal solution. Optimal solution. Right? So this is how the knapsack problem is solved by using branch and bound technique. Here, given n items of known weights and known values. Given 4 items of known weights and known values. We are going to pick the items for the knapsack in such a way that they should fit in the knapsack and should give more value. So only I found 2 items, 2 subsets from this set given, which will satisfy that constraint. Fit into the knapsack and that gives more value. Those are item number 1 and item number 3. So here is a solution. Let's take one more example. the nodes and find out what are the items selected for the knapsack. So right here, items selected for knapsack equal to, write a list here. So only with are to be considered, not without. This is without, leave it. This is with 5. With 5. So write 5 here. Write 5. Next, backtrack. This we got it from here. This is without 4. Leave it. Next, sorry, this is with 3. With 3. Write 3. Next, this node we got it from this node. And backtrack. This is with 2. With 2. And next with 1. So 1, 2, 3, 5 items are to be selected here for the knapsack, whose total capacity is 15. Okay. So 1, 2, 3 and 5. Calculate the total weight and check whether it is equal to 15 or not. Here I got 15. Check. Item 1 weight is 2. Item 2 weight is 5. 2, 5, see. 2, 5, 3, 5. 2, 5, 3 and then 5. So 2 plus 5 plus 7 plus 1. Right? 7, 7. This is equal to 15. Right? Total weight is 15. Here is also 15. So 15 is the total weight. Total weight. Right? I obtained 15 here. And the total knapsack capacity is also 15. Right? So both are matching. Next, I need to find out whether it is giving me this 94 as a cost or not. So for that sake, we add up all the profits here. 18, 40, 35 and this 2. Right? So here it is 18, 40, 35 and 2. Right? 8 to 10, this is 15, 4, this is 8 and 9. So here it is. Somewhere went wrong. 8, 9, 10, it is 15 here. 18, 40, 35 and 2. Here I got 94. Let's backtrack and check here. Backtrack and check here. I should get 95, whereas I got 94 here. We check. We check from this node. Right, we check from this node. Weight is 14 and the value is 92. This is value is 92 plus weight is 15. 15 minus 14. 15 minus, for this node we check. 15 minus 14 multiplied by, this is for node number 4. Means item 4, item 5th ratio I need to consider. So 92 plus this is 1 into 2 is 2. So this is 94. This is correct. 94 is here. Next, here we'll check. W equal to 15, B equal to 94. This is 94 plus W is 15 minus 15 multiplied by, this is for, this node is for 6th item. 6th item ratio is to be considered. This is 1. So 94, 15 minus 15 is 0. This, so this is also correct. This is also correct. Next, weight is 15 and value is 94. This is 94 plus 15 minus 15 multiplied by multiplied by 0. So it is 94 only. So here I got 94. Check whether this is 94 or not. So now for this we'll check 14 and 92. So 92 plus 50 minus 14. For item 3 we are writing. So item 4 ratio I need to consider, which is 2. So this is 92. 15 minus 14 is 1. 1 into 2 is 2. This is 94. This is also correct. So here itself, please that is verify. Here I should get 95, whereas got 94 here. So check these steps again.